Vertical stretch and compression of a quadratic function is determined by the number that is multiplied by x squared. So this number a here is multiplied. To distinguish this from the shifts, vertical and horizontal shifts, in both cases that is a number being added or subtracted. Added or subtracted after squaring, or added or subtracted directly to the x variable. Cause vertical and horizontal shifts, respectively. But a number that's multiplied by the x squared does change the shape of the parabola a bit. So if we start with our basic y equals x squared, this passes through 1, 1. And it also passes through 2, 4. The first thing we're going to look at is y equals 3x squared. This is stretched vertically by a factor of 3. So this graph passes through, instead of 1, 1, 1, 3. We can see that one way to find some of the points on this graph is to hold the x value of a known point fixed and to multiply the y value by that stretch coefficient. So the y value of 1 on our original graph got multiplied by 3 to get us a y value of 3. The 0.24 went to 212, which is off of this particular graph, so we can't trace that one. If we look at instead something like this, y equals 1/5 x squared, now that x squared is multiplied by a fraction that is smaller than 1, then this is going to be shrunk by a factor of 1/5. So where we had the 0.11 on our original, we now have the 0.1, 0.5. I'm sorry, 1/5 or 0.2. And where we had the 0.24 on our original, we would have the 0.2, 4/5. So again, I'm multiplying my y value by that shrink factor of 1/5. We can see that the 4/5 is pretty close to 1. Right, if we trace this over to the y-axis, that looks like about 4/5, or 80% of the way up to 1. So the effect that this has on the graph is if the graph is stretched, that means that my stretch or shrink factor A is greater than 1. A is a large number. It doesn't have to be excessively large. It just has to be a number that's greater than 1. Then the graph is stretched vertically, but what we see is kind of like what you would see if you were to stretch a rubber band. Since the graph keeps going forever, and we are just looking at a fixed window, what we see is that it appears more narrow. Now, if the graph is shrunk vertically, that means that our a value is a fraction. What we say is it's a number between 0 and 1. So it's a small number. It can actually be a negative number, but if it's negative, we just think of the negative as being the reflection, and then we still just look at the number itself to determine the stretching or shrinking. The number itself without the sign, that is. So if this is a number that's between 0 and 1, then we would say that the graph is shrunk. And here we want to imagine if you had a parabola and an elephant came by and just stepped on it, put its big elephant foot right here, right? There we have an elephant foot. that the fixed window that we're looking at this in would just make the graph appear wider. So it's a little bit odd that a stretch, which you think of something growing, actually makes it appear more narrow, and a shrink, where you think of something getting smaller, is where it appears wider. But think of it as all being in the vertical, in the up and down direction that the stretching or shrinking occurs. We're going to now look at a graph that has a number multiplied by the x squared. And I'm going to look at the minus sign first. That minus sign makes it reflected about the x-axis, which has the effect on this parabola of just making it open down. And then the stretch or shrink factor is really just the numeric part, ignoring the sign. So the 2 is really the stretch or shrink factor. So this is going to be stretched by a factor of 2. Now, with these stretching and shrinking problems, we really can just go with the simple route of picking a whole bunch of x values and plugging them all in to find the y values and plotting points. But we can still use the 1, 2, 3, 1, 4, 9 pattern that's so helpful with rigid transformations. The only thing we need to do to use this pattern, because we know it's not going to follow this exact pattern, it's going to have a different shape. This is the pattern for y equals x squared. The only thing I need to do is come in and multiply these y values by my stretch or shrink factor. And I could even multiply them by the negative while I'm at it, since it might make it a little easier to draw the graph. So if we're having to modify these anyway, we may as well not have to keep track of the opening down as a separate transformation, so that 1 times negative 2 is negative 2, 4 times negative 2 is negative 8, and 9 times negative 2 gets me negative 18. So that the points I'm actually going to plot for this are 1, 2, 3, negative 2, negative 8, negative 18, even though that negative 18 is clearly too big, so, well, too small, but too large in absolute value, so we'll leave it out. Now this does not have any shifts at all, so the vertex is still at the origin, so we'll go ahead and plot that 0, 0 also, but there's no need to write that down. And then plotting relative to the vertex doesn't make a difference in this case, because our vertex is at the origin, and I use symmetry to draw on the other side, and then I draw my parabola. We can see that this does have that look that a stretched parabola should have. It does appear more narrow. It opens down. This turnaround point should always be a smooth turnaround. It should never be a sharp little pencil point, but sometimes when the stretch factor is there, it makes it a little bit harder to turn it around smoothly. And we have our stretched and reflected parabola. Combining stretching with shifts is something that should show up at some point in your mathematical careers, but it's a little bit beyond our objectives right now. Right now, what we're really after is being able to graph a parabola that has shifts and reflections, and to be able to graph a parabola that has some stretching or shrinking and possibly a reflection, but not to combine those two kinds of transformations together.